Well, thanks everyone for joining. Well, let's wait for another few more minutes. We tend to say Berkeley time is 10 minutes after, Bill. I'm not sure how it works at Illinois.
Yeah, that's oftentimes the case.
Yeah.
Probably it's more precise as you go from west to east, but I don't think Illinois has made it to the Japanese standard yet. For example,
right. Yeah.
My student told me, Yasutaka Narazaki told me that if he isn't 10 minutes early, then he considers himself late.
I think I lost that one. That's all gone. But yeah, let's start Illinois time. So we'll wait for a few more minutes. I think people are joining in, but I'm just conscious about time. Bill, shall we start? Is that okay?
Sure.
Okay. So thank you everyone for joining this Smart Infrastructure Series seminar. It is my great pleasure to have Professor Bill Spencer for the final lecture of the Smart Infrastructure Series, supported by ITS, Berkeley Center for Smart Infrastructure, and the College of Engineering. Professor Bill Spencer is the Nathan and Ann Newmark Endowed Chair of Civil Engineering at University of Illinois, Urbana, Champaign. I've known Bill for many, many years, and he's very well known in the areas of structural health monitoring, structural control, cyber infrastructure application, stochastic fatigue, stochastic computational mechanics, and natural hazards mitigation. Professor Spencer has published more than 700 technical papers, reports, including 2 books, and he has been selected as global highly cited scholar in civil engineering by Shanghai Ranking Consultancy and Elsevier. And I've seen a lot of papers by Bill. He led NSF George Brown Network for Earthquake Engineering Simulation, NEAS System Integration Project, and I know other NSF-funded initiatives. And he has received numerous awards, including the ASC Outstanding Instructor Award, Normal Medal, Hausner Structural Control Monitoring Medal, Newmark Medal, many, many others, as you can see from his resume. He's a fellow of ASC, former member of the Chinese Academy of Engineering, former member of the Polish Academy of Sciences, the North American Editor-in-Chief of Smart Structural Systems, Executive Managing Director of the Journal of Earthquake Engineering and Engineering Vibration, and the past president of Asia Pacific Network of Centers for Research in Smart Structures Technology. Bill, thank you very much for agreeing to give this lecture to our colleagues at UC Berkeley. and the floor is yours.
Thank you, Kenichi. If you let me have the screen, I'll go ahead and share.
Yeah.
There we go. So I'm really happy to be here. Frankly, I would be happier if I were there with you and it wasn't the COVID environment and that we had to do these virtual seminars. But I thank you for the kind introduction and giving me the opportunity to participate in this seminar series. I might note that at the bottom of my slides on the right, there are page numbers. And if any of you have questions, if you note the page number, then I'll be able to quickly go back to that page and respond to your question. So the outline of my presentation today is as follows. First, I'll give you some background and motivation for this work. Then I will talk about the static monitoring. And then I will, just a second, they wanted me to pin my view up there. Let's see if that works better. Okay. Then I'll talk about dynamic monitoring using computer vision. I'll discuss several applications in field applications, and then ongoing research activities, and then finally some conclusions. So let's go ahead and get started with the background and motivation. Vision is truly an incredible feat of natural intelligence. More of the human brain is devoted to vision than anything else. Now, to understand how difficult the challenge is to use a computer to do vision tasks, let's look at this first photo. And I ask you, what is this? This photo is of a double-decker bridge. The top deck is for railroad, the bottom deck is for vehicular traffic. And although it's not that clear a picture, most people would be able to identify this truss bridge. This is what a computer sees. It just sees an array of numbers. And so the goal of computer vision is to extract useful information from this array of numbers. So I think that really puts things into perspective, that this is not an easy thing to do. Moreover, we have to worry about pixels and resolution. That is, the more pixels that we use, the higher the resolution, the clearer the picture, but the more data that's associated with each of our images. What you see on the left is that there are, the top left, there's 1200 by 800 pixels. That's about 1 million pixels, but for each pixel, there's 24 bits of color information. So it makes it about 23 million bits of information. If we reduce the information in each image, then the resolution goes down proportionately. And when we talk about video, each of those images, those 23, 24 megabits of information go into time. And so if you're talking about collecting video at 30 frames per second, it's a huge amount of data to analyze. Now, let's look just to see where we've come to today. Let's look at where this all started. In 1966, Minsky assigned computer vision as an undergraduate summer project at MIT. And then they were looking to try and interpret the synthetic world by looking at shapes. So by taking and saying, okay, this is a column, or this is a block, might be associated with a building or a roof, but how do we interpret these images? In the 1970s, progress was being made toward taking a scene and then partitioning it into, in this case, the sky, a building, a tree, the road, the underbrush, etc. And then there was a shift toward mathematical rigor, and artificial neural networks in the 80s. They came and they went. Now, what was the problem? Well, this in 1985 was the mainframe on the University of Illinois campus. For the entire campus, it was an IBM 4381, and it had a total of 24 megabytes of memory, not gigabytes, 24 megabytes. So the reason that neural networks came and went is because there just wasn't the computational power to drive them. Then there were a number of statistical applications that came into vogue, like facial recognition, which could be viewed as one of the primary apps or a killer app for computer vision. And then in the 2000s, broader recognitions, annotated data sets, video processing starts. And this was driven by huge advances in computer power. Now, this was is an old Apple Watch that I had. I think it's an Apple Watch 4, and they're on Apple Watch 7 now. But it had way more computational power than that IBM 4381, which was the mainframe on the University of Illinois campus. And combined with improvements in the algorithms, GPUs, there was a large increase in deployed vision systems to where today we have the promise of smart driving cars, autonomous robots, and who knows, maybe the great robot rebellion. Well, all of this was also driven by the evolution of digital cameras. What I want to show you here is the first commercial digital camera had 1,000 pixels. 1,000 pixels, that's like 30 pixels by 30 pixels. So if you recall back on that resolution slide that I showed you, this is almost useless by today's standards. Then the first commercial digital handheld camera, this Fuji DSX, cost about $20,000. And then subsequently, the Logitech Photoman, the price came down to $995. And then the Canon EOS DSC-1, $36,000. We're getting up to where this is commercial photographers were starting to use these digital cameras. And then while it may not be for sure that this was the first, but this Sharp mobile phone was one of the first digital cameras that was embedded in a smartphone. And then you've got the iPhone X, that's a few years ago, but this Canon D3500, only about $497. So the price per pixel has gone down dramatically, making applications using digital images much more accessible. So computer vision and structural health monitoring. As you know, manual visual inspection is still currently the main form of assessing the condition of civil infrastructure in the US and also throughout the world. And so using computer vision for SHM is a natural step forward and can be readily adopted to aid and eventually even replace manual inspections while offering new advantages and opportunities. So let me just give you an idea of what can be done using computer vision. And I'm going to look at what I call static monitoring applications. And it's especially nice to be able to give this talk here today because one of the first places that I saw computer vision applications was by Professor Soga when he was at Cambridge University. So the idea is that there are a lot of subways, they're called tubes in the UK. And one of the critical issues is being able to monitor the tunnel lining and to detect any changes. And so Professor Soga mounted this array of cameras on a flatbed trolley, and then it would move down the tunnel, taking a series of synchronized images that could then be reconstructed in a database and then queried at a later date. So imagine that you're going down, you're the tunnel inspector, you're looking in the tunnel, and you take your mobile phone and you take a picture of something that you think is a little bit odd. And so then you can register that image in the database. So, whoops, that wasn't supposed to happen. I thought I had my pointer ready. Let me set that. Laser pointer. So you can register this image in the database of the tunnel, and then you can get a binary change mask. And if it's entirely black, that means that the image before and the image now is the same. But if you see a difference as shown here, then that would indicate that indeed there's something different there. Well, others have also gone on and used this idea. This is some work in Germany. This is a retaining wall in Germany, work by Hallerman. And the idea is that they can use a drone instead of cameras on a trolley to fly a survey of this retaining wall. They then artificially damaged certain regions. They took and put the what looked to be something different, and they wanted to see if they could detect those locations on the on that retaining wall. And indeed, they were able, using change detection with computer vision, they were able to determine that these locations were different. And so that gives the idea of using this for periodic monitoring. Other ways that computer vision has been used, it's to identify the location and the length, the width of cracks. This is some work of a visiting student from Tsinghua University, Yupei Liu, when he was at the University of Illinois. And then we looked into the possibility of applying this with the US Army Corps of Engineers, where you could take an image and then by appropriately processing that image, you could extract that there are cracks here, and then you could get both the length and the width of those cracks. Other work, this is by Professor Shirley Dyke's group at Purdue University, where they're looking at doing damage classification to assess through pictures that were collected either in person or online, whether one has collapse or one has non-collapse, whether there's non-structural damage, etc. And this is another one of her applications. What she wanted to do was look at the possibility of doing an inspection with a drone. And in particular, they were interested in the welded joints on this truss structure. And so they've got 118 welded joints, and they flew the drone survey and then could identify the joint locations and then put that in a database so that the inspector could virtually look at each of the joints on this structure and make an assessment of if there were any differences, any changes. Now then work has been moving on to damage segmentation. That's where each pixel on an image is classified based on some sort of on a neural network algorithm. And so in this case, that dark red is corrosion. We have spalling is the light green. And so one identifies those and then feeds them into a neural network once you have enough images. Now, this particular damage segmentation data set, I think it cost me about a dozen pizzas. I got my group together and we labeled images all evening. And so you can see here there's images of concrete cracking, spalling, exposed reinforcement, corrosion, fatigue cracking, asphalt cracking. And this data can then be used to train networks to identify these types of damage on structures. But sometimes you may need to help the algorithms. And so some work that Vedas Haskari, who's now an assistant professor at the University of Houston, did was to provide context for those images. And let me explain in more detail what I mean. On the left is the original image, and on the second column is the scene and the building. So the idea is to identify what's the building, what's the doors, what's the sky, and don't detect cracks in the sky. Don't detect cracks in the doors or the windows, because those are non-structural elements. And then you can detect in this third column the presence of damage, superimpose it on the scene of the building, and have a higher level of recognition of the damage that's being identified using these computer vision methods. Well, let's move on and talk a little bit about some dynamic monitoring. One of the things that's kind of fun is to do vibration testing using optical methods. This is optical flow. A KLT tracker tracks each region, each floor on the building. And then once you have those time histories, you can go ahead and do classical modal analysis, experimental modal analysis, estimating the modes, the frequencies, even the damping. And this figure shows a comparison between that camera, the still camera operating at 60 hertz, and an accelerometer with 64 hertz. And so you can see that this has great potential for vibration testing. Another interesting piece of research came out of MIT. It's called motion magnification. And the idea is that you zoom in at a certain frequency and then amplify the motion at that frequency. Now, I want to just show you this. I'm going to take this out of pointer mode. This is an image of a guitar, and it's actually a video. But do you see any motion there? You can see that it's playing, but there's no motion. The displacements are too small. So let's go in, and this is still a video. So I've blown it up. You might have thought, oh, that was just too small. You couldn't see it. But if I use motion magnification, what you see here, these are both videos, but through motion magnification, you can see that that top string on the guitar is indeed moving. Now, what we did in my course was to take and use this to demonstrate the principle of modal decomposition. So on the left is a structure. Maybe it's not so easy to see it vibrating here. In this enlarged version, you can see the motion of the structure. And so if we use motion magnification and we decompose that motion into the behavior at each of the modes, you can see very interesting results. The first mode is indeed large. The second is okay. But in that particular response, the third mode is extremely large. Now, okay, I cheated a little bit. I wanted to demonstrate that the third mode was larger. So we plucked it in the middle instead of it being shaken at the base like it might be for an earthquake. Well, there are other applications, and this is one for we call it the Little Golden Gate Bridge, or Muhammad, the city where it's located, calls it the Little Golden Gate Bridge. It's a pedestrian footbridge. It's 67 meters long, and we flew a UAV drone survey. This is the video of the drone in behind those tree branches. And this is the actual drone footage. Now it's sped up by a factor of 2. But what we did was a divide and conquer. We took a picture with the drone here, then we moved it down and took another picture, video sequence with the drone. And then we pieced it together to be able to get the mode shapes of this structure. And you can see the comparison between the accelerometers and the UAV drone survey is quite good. One thing I want to tell you about now is just to illustrate some of the things you can do. We have a new smart bridge at Illinois. The grand opening is a week from today. It's between 2 of our buildings, our Hydrosystems Laboratory and the Newmark Laboratory. And what we wanted to do was to investigate the pedestrian bridge traffic. And so by using a single camera, we're going to have 2 cameras eventually so we can triangulate the motion, but we can take the video, process it in real time, and on the left is the actual video, the right is processed, and then that's superimposed in a virtual environment. And on the right, you can see we can track the location of the individuals on the bridge. So we'll be able to anonymize the video because we won't show any faces. We'll just show these stick robots. And then we'll be able to track the location of the individuals on the bridge. And so that's one of the loading cases for the bridge. Okay, let me tell you something about some large scale applications, not just laboratory applications. And the first is railroad bridge monitoring. This is a railroad bridge, a freight railroad bridge in northern Illinois. And it happened that the trains only came across at night. So we set up our video cameras and had some large lights. And these are some of the images we took for the horizontal and the vertical deflections. And I think if you look at that, you have a hard time seeing the motion of those bolts on there. Those were natural features that we selected, but it's hard to see any motion whatsoever. But applying computer vision using this KLT trackers, optical flow, you can see here, this is a comparison between the finite element simulation of that truss bridge and the measurements that we got from the computer vision, the optical flow. And you can see that they're quite good. Now, you might note that they're better at the beginning, and at the end, there's a little bit of a time difference between the peaks. And that was because we ran our train at a constant speed in the simulation. But in the real train, there was a curve in the track right after the bridge. And so what happened was, as soon as the bridge started going over, as soon as the train started going over the bridge, it began slowing down. And so that resulted in a little bit of a time difference towards the end of the crossing. Now, we've also looked at the possibility of having drones monitor the displacements of bridges. And so this is a drone in the laboratory, and on the lower right is the video from the Phantom 3. You can see it moving, and there's a hydraulic simulator in the background that you can't even hardly see from here, more or less detect that there's motion that's going on. But nonetheless, the video processing of the images from the drone was able to determine what the displacements were for that bridge. And you might say, well, why are you interested in those displacements of bridges? It's because when a freight train goes over a bridge, if that bridge doesn't move very much, that's a good indicator. The railroad engineers believe that's a good indicator that that bridge is quite healthy. So if one can routinely monitor the displacements of the bridges, that can be an indicator of the bridge's health. Now, this is some work of Professor Mani Gopalvar-Fard. It could be used for railroad bridge applications or also for highway bridge applications. But he is at the University of Illinois in our construction management group and doing some great research. So he has developed some approaches where you define the mapping region. You then use a UAV to you plan your trajectory and then use a UAV to survey that bridge. And you can then evaluate the visibility, the resolution, the orientation, and then to automatically detect defects and characterizations. And he's working with researchers and engineers in Japan to implement this. And I believe that he's already deployed this. He's already done over 30 UAV surveys of bridges. Now, another area in the transportation domain is the inland navigational waterway system, the series of rivers and locks and dams in the United States on the Mississippi River, the Ohio River, the Columbia River. And that's monitored by the U.S. Army Corps of Engineers. And we do a lot of work with the Army Corps of Engineers. And one of the things that we were looking at is this lock and dam on the Columbia River. It's called the Dalles. And if you look on the left, there's a video, and that boat is going down. These locks on the dams are like water elevators. And this particular lock and dam, if you look at the chamber, it's 200 meters long, 26 meters wide. And the gate is 33 meters tall. So it's a huge steel structure. And they found that there were cracks along near the pintle along which is the bottom hinge on the south gate. And they found this by an underwater robot. And they asked us if we could help with the model updating to be able to better understand what might have caused that particular crack. And so we went down there and did a photo survey, not a video survey, because this takes maybe 20 minutes for the water to be lowered and the gates to open. So it's not a dynamic situation in general. And we did a photographic survey with high resolution cameras. If you look in the red here, those are what we use to normalize our photos. The wall is not moving. We'll call those static images. And then the non-static images are the yellow boxes. They were weld access holes that were easy to identify. We did have some trouble because over 20 minutes, if the sun went behind a cloud, it would cast shadows and would affect the computer vision assessments of these displacements. But by and large, we were able to identify the motion of the lock and while it was being loaded, while the water level was increasing. And these are currently, this information is for these various points is currently being used by the Corps to do model updating, finite element model updating in Abacus. Now, I want to talk to you about smart construction management. This is also some work of Professor Golpavar in our group. And he talks about, I think this is really some cool stuff, that it's a 4-dimensional BIM, not a 3-dimensional BIM, that is going to include as-built documentation, progress monitoring, quality control, safety monitoring, and then eventually the contractor handover. So what does he have in mind? Well, this is the Sacramento Kings Stadium. This is actual drone footage during the construction process. And so the idea was that once or twice a week, one would fly a drone survey. And then one would create a 3D point cloud from that drone survey via the images that were acquired. They would be registered against the physical images. And so the BIM and the point cloud are jointly connected together. Then one can create 3-dimensional synthetic renderings of the environment so that you can do queries and look at information, with the ultimate goal of answering the questions of who does what work in what location at what time. And so in this way, you can have a good assessment of the current state of the progress for the project, and then that's color-coded in the 4-dimensional BIM. And I've got one more application that I'd like to show you before turning to some of our recent research. And this is on post-earthquake, rapid post-earthquake assessment. The 2017 Central Mexico earthquake occurred on exactly the same day as the 1985 Mexico City earthquake. And so this was a large earthquake, and as fate would have it, there were a lot of people displaced. 361 reported casualties. Over 10,000 buildings showed signs of damage. And one of my former students, Professor Manuel Ruiz Sandoval, he's now the department head at University of Mexican, Universidad de Metropolitan. So he is the department head there. And I called him up and I said, we'd like to come down and do some drone surveys. Can you help us get permission? And he said, you don't need permission. Mexican's a free country. And so he was joking, but he helped us come down there. And the student on the right with the orange hard hat, that's Vedas Hastere. And so they were helping out with the inspections and used drones for a couple that one that I'd like to show you in particular. So the number of buildings that needed to be inspected were about 10,000, as I said. There were about 1,800 that the initial safety reports indicated were undetermined risk. And then on October 11th, there were still 327 that were of undetermined risk. And so what resulted was that a lot of people were homeless. They couldn't go back to their homes until the structures were inspected. So this particular building in the background, we wanted to validate some of the work that we'd been doing, that Vedas had been doing. And so he planned out the video path, the UAV path as shown in the figure on the right. And this is on the left, some actual video footage. And you can see on the right then the resulting 3D point cloud that was generated from that. So you took the video footage and then you could create something that is at least in the computer, it's tangible. You can rotate, you can pan, you can assess what is going on. But that's maybe not enough. So what he did was he further did damage identification on the images. And you can see here, he's able to assess cracking and spalling and building openings, debris, etc. Now, the problem is that if I asked you, is this damage serious? Well, it looks pretty serious, but it depends on where this photograph was taken. And so what we did was we superimposed that on what we call a condition-aware model, where we can do a virtual inspection with the damage already labeled. So it brings the attention of the engineers to the locations that are critical. Indeed, this is how a lot of medical imaging is done these days. If you go in and have an MRI or a CT scan, computer vision will identify the anomalies so that the doctors don't miss anything. It brings them to their attention. So that's a similar thing to what's happening here. So using these condition-aware models, the inspector can quickly query portions of the structure that are high damage, and then visually inspect those regions to assess safety. Okay, let me move on to some of our more recent research. And that's on digital twins enabling post-earthquake inspections. And first, I'll talk about the building applications. So first of all, what our digital twins have embedded in them are what we call a physics-based graphics model. And the idea is that we want to create a 3D synthetic world in which the digital twin lives, and we can damage that digital twin and then investigate various inspection scenarios, but it's a living digital twin with the structure. So the idea is that we start out with a graphics mesh or a graphics model of the structure. We use that to build a nonlinear finite element analysis of the structure. Then we can investigate various damage scenarios from that finite element model and create associated masks that can then be superimposed on the structure. So we create textures that represent that damage. They're applied to the structure, and then we have this 3D synthetic environment in which you can ask questions about, well, what if you fly your drone whenever it's cloudy? What direction do you have to point your cameras? What if there's a tree in the way? How can we avoid that tree? So all of these questions can be asked in the computer, with the central thesis is that if you can't do it in the computer, you're probably not going to be able to do it in the real world. And the real world is a lot more complicated and a lot more costly to crash a drone. So we've done that. We were doing some work on a lock and dam on the Mississippi, on the Mississippi River. And the drone went down in the locked chamber. It lost contact with the GPS and it crashed. So you can just hit the reset button if you crash a drone in your synthetic environment. Well, we're applying that idea to 2 twin apartment towers in Guangzhou, China, with the idea that we'll be able to use this digital twin to create flight paths that, should an earthquake occur, we could immediately deploy the drone, survey the building, and make an assessment of whether significant damage has occurred or not. And this is work that is being done through a grant from the National Natural Science Foundation of China and several faculty, Jingjing Wang and Professor Liu and Professor Jie Cui at Guangzhou University. So we have weekly meetings. COVID has enabled, it's certainly been painful, but it's enabled collaboration that probably wouldn't have been possible otherwise. So we have weekly meetings and have been moving this along quite effectively. One of my other students, who's now on the faculty at the Zhejiang University, University of Illinois campus in Haining, is interested in high-speed rail applications. And this is a map of the railway network, the high-speed railway network in China, and you can see it is extensive. And so most of these railroad bridges are elevated, or let me say this again. It's the second longest network in the world, and much of the track is elevated, as shown here. And so you may have over half of the rail that is elevated, or that is over half of the rail is a bridge. And so the effective management of this rail infrastructure is required to maintain safe, uninterrupted, and sustainable operations. So Yasutaka and our group envisioned creating a synthetic environment that will allow one to do bridge component recognition and localization, that one can then do vision-based UAV navigation and vision-based UAV structural assessment, and then to actually fly the drone surveys in the computer to try and in this synthetic environment to assess whether it's going to be effective or not. So one can build digital twins of your infrastructure and then use that to assess the potential that these UAV surveys can be effective. In this particular case, because the damage is realized in the computer, you have automatic labeling. Labeling is a really challenging task. You have automatically labeling of the images. And so on the left, you can see the synthetic images, and on or let me say that again. On the left, you can see the actual images, and then using this automated approach, the components were identified and then damage was localized. Now, this is a prototype of the system for actually doing the autonomous navigation that I mentioned to try and find optimal paths. And you can see the path that the drone is taking on the center screen, and on the left is the synthetic environment. And so the right shows a 3D version of how the drone is navigating. So this enables field implementation of autonomous inspections using these unmanned aerial and ground robots. So with that, I'd like to draw some conclusions. First, research on computer vision-based inspection and monitoring of civil infrastructure is advancing very rapidly. And so time-efficient, cost-effective, and eventually automated civil infrastructure inspection and monitoring will be enabled, heralding a coming revolution in the way that infrastructure is maintained and managed. And implementation of this research will ultimately lead to safer and more resilient cities throughout the world. However, if you note that computer vision, machine learning are not in the undergraduate curriculum of a standard civil engineering program. So the future is going to require uniquely trained engineers to integrate these innovations in emerging technologies to provide more resilient societies. To that end, Professor Hui Li at Harbin Institute of Technology and I partnered with ANCRIS, the Asia Pacific Network for Centers in Smart Structures Technology, and took advantage, let's say took advantage, but the COVID environment to create what we call the International Competition for Structural Health Monitoring. We did this in lieu of the international summer school that we would typically run every year. It was it was going to be at Purdue University and it was canceled. And so we decided to have this online competition. And there were 57 teams of researchers from a dozen countries, as you can see here, that participated in 3 projects. The first was image-based identification of fatigue cracks in bridge girders using real data from bridges in China. And then data anomaly detection. A critical thing for structural health monitoring is knowing whether your data is good or if it has some sort of faults in it. And then the third one was condition assessment of stay cables on cable stayed bridges using tension measurements from the sensors that were implemented. And this was hugely successful. We had a lot of teams that ended up publishing their work in a special issue of the Journal of Smart Structures and Systems. I'd be glad to point you to that if you have interest. Well, that led to the second international competition for structural health monitoring. And this was, we took on 2 partners, Veda Saskari at the University of Houston and Yasutaka Narazaki, who's in ZJU, UIUC in Haining. And there were, again, 3 competitions, but we used these synthetic environments. So one was for bridge inspection. One of the competitions was for bridge inspection. So using these images to identify the components on this bridge and damage. Another was for building inspection, again, using these 3D synthetic environments. And then finally was for vibration measurement and damage identification. And this competition had 52 teams, again, from 12 countries around the world. We're currently evaluating their contributions now. But this is really a great way to advance the field of computer vision for civil infrastructure inspection and monitoring. Next year's competition is going to be led by Tongji University, but as you know, they're a little behind based on the COVID situation in Shanghai, but I hope to have more to tell you about that in the near future. So with that, I'd like to welcome you to the University of Illinois at Urbana-Champaign if you're in the area. And thank you for your attention. This is my contact information, and I'll be glad to take any questions that you might have.
Thank you, Bill, for a very enlightening talk. I'll invite some questions. I see Champaign.
Hi, thank you, Professor Stensai, for your excellent work. I'm Xin, and I'm currently working in building an autonomous UAV platform for structure inspection with Professor Rajasen Gupta. I have seen your team has done some excellent work in autonomous UAV navigation for structure health inspection. And I'm wondering, what's your opinion or insight about the building information system or digital twin for the role of those parts will what kind of role of digital twin can play in the autonomous inspection path planning, if it is possible for it to help UAV to make a technical decision like the professional civil engineer.
Thank you for the question. And indeed, your work is very valuable. This is a huge field and there's a lot of opportunities to contribute. Let me just say a couple of things. First of all, almost all of the work I showed you they identified the damage, but they didn't tell you what the meaning of the damage was. They didn't tell you, is this a column on the first floor, the second floor? Is this a red tag building? Is it a yellow tagged? Is it a green tag building? So the ability to take that information and make decisions, that's still a huge gap in these computer vision methods. And so what do you need to make that connection? Well, you have to know what that structural element is and what its role is in the structural system. So one of the ways to do that is through the BIM, where you can take and you correlate the image that you see in the video or in the image, the structural component you see in the images, you correlate that to the element in the BIM, and maybe you have a finite element model which is associated with that. And then you'll be able to make decisions or move closer to being able to make decisions, whether that's through the help of an engineer or whether it's getting closer to an automated assessment.
Thank you very much.
Thank you for the good question.
Thanks, Shane. Any other questions from my colleagues?
This is so cool that people can attend from anywhere. I mean, not only is she in California, but it appears that she's out enjoying the weather at the same time.
Any other questions from my colleagues? Andrew?
Yeah, excuse me. Thank you so much for your presentation. I had a question about sort of leading towards adoption of this technology in practice. As the cost of cameras, as you highlighted, has come down and their performance has raised, as well as now a lot of personal use drones have become much more affordable. For engineers just entering the practice or those that have been established, are there tools that they can adopt some of the computer vision methods that you've highlighted here into their own practice, or is this still in the research stage?
There's a lot of companies out there that are selling tools and pushing technologies. And so if you have a nail and they have a hammer, then you're in great shape. But that's the question you have to ask is, do you have a screw or a bolt and they have a hammer, and will it meet the needs of your particular application? So I think there's still a lot of development that needs to be done. And let me just point out that there might be one of the kind of the breakthrough applications is in the, I believe it's in the San Francisco area, you can get pre-approved inspection plans. I don't know if you know about this. It's a private medicine these days where you can have a doctor and you pay like a fee every year, and that means you can go see that doctor anytime. They only have a finite number of patients. And so this is maybe going to be extended to building owners where they have a engineer that is their engineer. If there's an earthquake or an event, that engineer is going to come right to their building and do the inspection immediately. Well, imagine that engineer, before the earthquake occurred, he took a drone and had a pre-planned drone survey that as soon as it occurred, he could send out a couple of drones, inspect the building, and use that to make an assessment and either let you back in your home or your office as quickly as possible, or tell you, no, this is dangerous, you better stay out. But it's that rapid assessment. Now, you can't see inside the building, but in general, inspectors don't go inside the building on the first survey anyway. They're going to be looking at exterior information. And so the big advantage of the drones and also this what I would boutique medicine idea is that people are going to have these tools where they're going to say, I'm going to inspect your building and have you an answer within 1 hour of when the earthquake occurs. And that could be quite enticing to individuals. So that's the type of niche area that I think, as opposed to trying to sell this to the Department of Transportation, which is typically very, very conservative and slow to adopt things. So those are just a few thoughts in that direction, Andrew.
Thank you so much.
Thanks, Andrew. Any other questions? I see Tao.
Hello, Professor. Yeah, thank you for your presentation. And I see.
Oh, where are you? I don't see you.
Oh, I'm in Berkeley right now. I'm actually in the computer lab right now.
Oh, yeah. There you are. I couldn't see your video, so thank you.
Oh, can I see my video? Oh, okay.
Oh, now I can see your video.
Okay, cool. Yeah. So I see you have done a lot of research in like computer vision to detect the structural damages, and both of those techniques that are based on labeled images. And I know it's a very challenging task to gather and label those images, with a very great accuracy. Yeah, and I'm wondering, yeah, actually I was the labeler like many years ago. Yeah, and I'm wondering if there's any research right now, like trying to use like unsupervised learning techniques to detect those damages. I know this is very challenging, but I'm just wondering if there's any progress right now. And yeah, thank you.
Certainly that is an area of coming up with algorithms that you can, or self-learning, you might want to think about that. So, but let's say that I put you in a room and I ask you you didn't know anything about Python and I asked you to learn about Python. You'd eventually figure it out. But let's say that I now give you an instructor or a tutor to help you learn about Python. You're going to learn a lot faster. And so it's a question of, do you want your algorithm to sit around there and take a long time to figure things out? And that's good, but it may be better to do some initial training and then use these unsupervised approaches to refine the methods. So if you already know the basics of Python, then you can figure a lot of things out on your own, but it would be much more helpful if you got the basic ideas. That's the first thing. And then the second thing is that there's a good bit of work these days on combining synthetic images with real images and using those synthetic images, which the synthetic images can be automatically labeled. And so you don't have to sit around and identify the damage and what's the trees and what's the brush. So they're automatically labeled, and they can be combined with real images to be able to do the identification. The work of Yasutaka Narazaki used entirely synthetic images, but he showed that he could get very good recognition of the real images for the cases he considered. So there's a couple of possibilities there.
Yeah, thanks, Tao. Bill, there's one question on chat. Jin Yan says that, thank you for the great talk. I hope to ask if there's any UAV or other computer vision application for indoor monitoring and inspection. I assume it might be hard to deploy UAV indoors, but you start to see them coming inside as well.
It seems to me that I've seen that already. I can't point to it, but there was a UAV that would be docked, and then it was like for security monitoring in your home. And yes. So in that case, it can use optical flow. They have the sensors that would be pointing at the floor. And I don't remember the details. Maybe you've seen that, Kenichi, but I'm pretty sure that that's out there, and that eventually that will indeed be a possibility in your home too.
Yeah, thanks, Phil. Now you're saying that our future generation need to learn computer vision and that sort of new technology. Do you think we should put that in structural engineering courses? How do we embed it in our courses rather than having a special course or a special one? It would be great to integrate to our course materials.
Yeah, I think the challenge is that we have to integrate it into the professors, so they have to learn it first before they can teach it. So that may be a higher hurdle. Yeah. But we've got a new course on data science, which includes in civil engineering. It's a senior level, first year graduate student level course. And it talks about not just computer vision, but a wide variety of data science issues, introduction to machine learning. And so, at one point, probably when you and I were undergraduates, we actually had a course on maybe Fortran or C or something like that. And so they taught us computing, but then eventually that became so pervasive that they just assumed that you knew these things. So at this point, we're going to have to teach people about some of these topics so that they are not afraid of them, they embrace them. And then eventually we'll be able to integrate them into the other courses. But this data science class is one of the most, we've got two courses. One's on data science and one is on sensing and instrumentation. And that's those are two of the very popular courses that we have for our undergraduates now.
Yeah. Oh, thanks. Yeah, at UC Berkeley, we also introduced infrastructure sensing and modeling course for undergraduate. And so we are going the same direction, Bill. Well, now it's 5 o'clock our time, and it's 7 o'clock or 8 o'clock your time. Is it 7, I think?
Yeah, 7 o'clock.
Yeah, so Bill, thank you very much for the enlightening talk, and the advances in computer vision technology in the past 10 years being amazing, and you illustrated the excitement in this area very well. And I'm sure that my colleagues got more interested in this area from your talk. So Bill, I know it's early Friday morning, 7 o'clock now, and thank you again for spending your precious time with us.
It's my pleasure. I might just comment before people leave is that in the chat, Mr. G. Kong put the link about this building resumption, what was it called, the guidelines for the building occupancy resumption program. And so there's a lot of synergies there for the future.
Yeah.
But nonetheless, thank you again for giving me this opportunity. And I sincerely hope that we can meet soon in person.
Yeah. So that was Grace Kang from Peer, who uploaded that particular. Thanks, Grace. And so please join me to thank Professor Spencer for his talk. Thank you very much, Bill.
Thank you.
Yeah, and first of all, well, thank you very much all for participating this smart infrastructure seminars we had this semester. And if you missed any of them, you can go to the ITS website to view them. So please do so. And they're excellent talks like we had today. Bill, thank you very much. And then hope you have a good weekend. And then everybody, goodbye.
Okay, thank you. Bye-bye, everyone.